So at this point we've talked about several parts of the periodic table. We know how to use the table to find types of electrons in an atom where they are. We've used it to describe the properties of atoms in the groups and different sections of the periodic table. But what else can we learn about the elements from just looking at the table? Well, there are several things that we can look at called periodic trends, and these are patterns that we can find on the table. In order to talk about these trends, we need to define 4 terms. The first term is atomic radius, and this is going to actually be the first trend we look at. The atomic radius is the distance between the nucleus and the outermost electrons of an atom. And this is basically a measure of the size of the atom. So whenever we talk about atomic radius, we are talking about the size. So if we were looking at this sodium atom, the atomic radius would be the distance between the nucleus and the outermost electron. So half the distance across the entire atom. The second trend we're going to look at is the first ionization energy. And this is the energy needed to remove the outermost electron from an atom. And it's important to remember that in order to remove an electron, to make an electron jump from a low energy level to a higher one, energy has to go in. So what we're trying to do is take this electron, this outermost electron, and actually make it leave the atom. So the ionization energy, the first ionization energy, is the energy needed to remove this outermost electron, the one farthest from the nucleus. The third trend we're going to look at is electron affinity. An electron affinity is a measure of how much an atom attracts electrons to itself. So it's almost the opposite of the ionization energy. So the ionization energy is really a measure of how easy it is to remove this electron right here. And electron affinity is how much an atom wants to gain that electron back. So if we have an atom that wants to gain an electron or needs to gain an electron, it will measure how easily that atom will attract the electron. The last trend that we're going to look at is called electronegativity. And electronegativity is a measure of how much an atom attracts electrons to itself in a bond. So for electronegativity, what we're really looking at is 2 atoms. So let's say we have an oxygen atom and a hydrogen atom. And when 2 atoms bond, they actually share electrons between them. So if I have these dots here, I'll actually draw complete Lewis structures. So if I'm talking about a bond between 2 atoms, electronegativity measures how much the electrons are pulled to one side or the other. Think of it as a tug of war. In the case that I drew with oxygen, oxygen is more electronegative than hydrogen, so the electrons are actually pulled towards the oxygen more than they are towards the hydrogen. So think again of a tug of war. If I have 2 people, and they're holding a rope, whoever is stronger is more electronegative. So whoever's able to pull the rope more towards one side is the more electronegative person, the stronger person. So what are the patterns on the periodic table for atomic radius? So we'll start with looking down a group. So if we look at the atoms going down from top to bottom on the periodic table, what happens to their size? So looking down, let's look at some of the energy levels of these atoms. So if I draw hydrogen, hydrogen has a first energy level of electrons. Lithium has the first energy level, 1s2, and then it has a 2s1 electron. Sodium goes up to 3s1, so it has 3 energy levels. And we'll do potassium. It actually has a 4s1 electron. So what do you notice happens to these atoms as you go down a group? Well, because we're adding energy levels, the atoms are getting bigger. So lithium's bigger than hydrogen, sodium's bigger than lithium, and so on as we go down. So as we go down a group, the atoms get bigger. Now let's look across a group. So we'll go from left to right. When we go left to right, let's look at, again, hydrogen. So hydrogen has 1 proton in the middle in its nucleus, positive charge, and around it, it has 1 electron. So it's 1 proton, 1 electron, and this is hydrogen. If we look at the next element, helium, helium has 2 protons in the nucleus. It also has 2 neutrons. And around it, it has 2 electrons. Well, if you notice I drew the orbital closer to the nucleus. And why is this? Well, positive and negative charges, protons and electrons, attract each other. So if I add more positive charges, so here I have 2 positive charges in the nucleus, they are going to pull on the negative charges more strongly because I have more positive charges. Well, I also added another electron, but the electron was added to the same energy level. Remember, if we move across a group, this whole row is the 3rd energy level. This whole row is the 4th energy level. Now, the D section here is actually the 3rd energy level, but that's even closer to the nucleus. But whenever we add electrons moving across the table, adding an electron every time, they go the same distance away from the nucleus, the same energy level away, as the previous electron. So our atoms actually get smaller when we go left to right across the table because we add more protons to the nucleus, creating a stronger pull on the electrons, which are all located in the same energy level. So one more time to summarize, when we go down a group on the periodic table, so from top to bottom, the atomic radius increases, the elements get bigger. And if we go from left to right across a period, our atomic radius decreases. So the way I like to think about the first ionization energy is to think about you holding something that someone else wants. For example, here's me, and I'm holding my pencil with my arm outstretched. If you want to take the pencil from me, it would be pretty easy to take the pencil. I don't have much strength to hold onto the pencil when my arm is far away. On the other hand, if I held the pencil very close to myself and you tried to grab it, I would be able to hold onto it much more easily. Atoms behave the exact same way. So let's again look at a simple atom. Let's look at hydrogen. Hydrogen has one proton in the middle and has one electron on the outside. Now, this proton attracts the electron towards itself, so it holds on to the electron. Now, if I pick a much bigger atom, let's say potassium, potassium has 19 positive charges in it. So, draw lots of positive charges. I'm not going to draw 19, I don't have room, but there's 19 positive charges in there, and there are 4 energy levels. Its outermost electron, because remember when we defined ionization energy, we said it's the energy needed to remove the outermost electron. Now, even though the electron is attracted by more protons here, it's much farther away. The atomic radius of potassium is much, much bigger than the atomic radius of hydrogen. Therefore, the nucleus cannot hold on to the electron as strongly as it does when the electron is much closer to the nucleus. And this is going to lead to our trend. So we can actually use the periodic trend of atomic radius to help explain the trends for ionization energy. So using that information, down a group, ionization energy decreases. And the reason for this is that the atoms get bigger. The electrons get farther and farther away from the nucleus as we move down a column on the periodic table. So therefore, it will take less energy to remove those electrons. So low ionization energy means that not much energy will be needed to remove electrons. Across a period, again left to right, ionization energy increases. And this is again explained by the trends in atomic radius. So because the elements become smaller moving left to right, the electrons are closer to the nucleus on the right side of the table compared to the left side of the table, and therefore there is a more strong force between the nucleus and the electrons, outer electrons, so it will take more energy to remove an electron. The nucleus is holding on to those electrons on the right side of the table much more strongly than they are on the left side, so it will be much harder. It will require more energy to remove those electrons. We can look at electron affinity in a very similar way to ionization energy. So electron affinity is how well an atom attracts electrons to itself. So let's say this again is me, and I want to pick up this quarter. Well, where would it be easier for me to grab the quarter? Well, if the quarter is really, really far away, I'm going to have trouble grabbing onto it. But if the quarter is very close, it'll be much more easy for me to pick up the quarter. What does this have to do with electron affinity? Well, let's again compare it to hydrogen. So in hydrogen, I have my one proton, and then the first energy level with an electron. If another electron passes by, so the electron's moving, the electron is pretty close to the nucleus. It's pretty close to this positive charge where it can be attracted. But if I have a larger atom, such as potassium, again, potassium has a lot of positive charges in it, so I'm just going to write K with a plus there. And this has 4 energy levels. So then protons, 1, 2, 3, 4 energy levels. If the same electron is passing by the potassium atom, where is it more likely to be attracted? Well, all the positive charges of the potassium are in the middle, 4 energy levels away from this electron. So the positive charges here have to attract the electron that's all the way out here, where the electron can get very close to the smaller atom. So what we find is atoms that are smaller tend to have higher electron affinities, tend to attract electrons to themselves more strongly than larger atoms. Therefore, down a group, electron affinity decreases. Because the electrons get farther and farther away, the nucleus of the atom is less able to pull on additional electrons. And across a period, again left to right, electron affinity increases. Because our atoms are getting smaller, electrons on the outside that pass by our atoms are more easily attracted to our nucleus. The final trend that we're going to look at is electronegativity. And as we said before, electronegativity measures how much electrons are shared, or how evenly those electrons are shared in a bond. We can look at electronegativity like a tug of war. So there are two sides both pulling on electrons in between two atoms. The side that is stronger, who pulls the rope more to one side than the other, is the more electronegative element. So here are several pictures of the electrons around an element. The larger it is, the larger the red area is, shows you where the electrons tend to be. So if we look at this picture, the electrons are more likely to be found towards the yellow atom than the blue atom. Down here, there's a big difference in electronegativity. The electrons appear more often around the purple atom than the blue atom. So the purple atom is more electronegative than the blue atom. And we can use the same logic as we used for electron affinity to figure out the patterns on the periodic table, going down a group and across. So down a group, electronegativity decreases. And this is just like before. When you go down a group, we add more energy levels to our atom. The atoms get bigger, so there's less pull of the outermost electrons, the electrons that would bond with another atom, the valence electrons, than there would be if the electrons were close. So the larger the atom, the weaker the pull of the nucleus on those electrons. And the same thing for across a period. Going left to right, electronegativity increases. Our atoms get smaller as you move across the periodic table, so the electronegativity of those atoms is going to increase. Now, there's one group on the periodic table that is a major exception to these trends. So these are exceptions to electron affinity and electronegativity trends. So what are these exceptions? Well, the exceptions are going to be the noble gases. Well, why don't these elements follow the same trends as the other elements? The reason is that they have a complete octet, 8 electrons. So they are not going to be attracting other electrons to themselves. So According to the rules of electron affinity, as we move left to right and bottom to top, fluorine would be very, very electronegative, which it is. It likes to attract electrons. But if we pick, let's say, helium, and we look at that, well, that's even more to the right and more to the top of the table. It actually never attracts electrons to itself because it has a complete octet. So because these will not gain or lose electrons, they do not follow the same rules for electron affinity. They also don't follow the same rules for electronegativity because they don't bond. If you have these elements that don't bond to anything else, you can't measure how much they share electrons in a bond. So these elements, with the exceptions of some of the larger ones, which we've actually been able to make a few compounds with, don't have electronegativity values. So now let's look at a sample problem, something that I could give you as an assessment on this material. We have three elements here: selenium, potassium, and bromine. And I want you to order them from least electronegative to most electronegative. If we notice, potassium, selenium, and bromine are all in the same row. So what do we know about electronegativity? Well, electronegativity increases going left to right. So the one that is going to be the least electronegative is going to be farthest to the left. So the correct order for these will be potassium will be the least electronegative, followed by selenium, followed by bromine. Let's look at one more example: arsenic, antimony, and phosphorus. So if we find these elements on the table, we'll notice that they're all in the same group. And the trend for electronegativity is that electronegativity decreases as we go down a group. So the least electronegative is going to be Sb, antimony, followed by arsenic, and the most electronegative of these elements will be phosphorus. So knowing all of these trends, periodic trends, you can learn a lot about elements when comparing them to one another. We can look at their size, ionization energy, electron affinity, and electronegativity. Soon we're going to use these trends, these facts about the atoms, in order to figure out how they are going to react with one another. Now let's just summarize our results for the periodic trends all together. So here's our periodic table, and let's first look at atomic radius. So going down a group, any group on the periodic table, what happens to atomic radius? Well, atomic radius increases as you go down a group. What happens when atomic radius when you move across the table, left to right? Well, across the table left to right, the atomic radius will decrease. The atoms get smaller. How about for first ionization energy? First ionization energy down a group is going to decrease, while going across the table is going to increase. Same thing for electron affinity. Decrease as you go down a group, increase as you go across a period. And electronegativity, it'll decrease going down a group, and it'll increase across a period. So there's actually only two patterns you have to remember. You need to remember that atomic radius goes up as you go down a group and goes down as you go across, and then all the others are just the opposite. So all of the other three trends decrease as you go down a group, increase as you go across, while atomic radius does the opposite.